So there's a lab today at 3, right? And you guys know the room from last quarter? Jay's lab. Okay. Okay, so we're going to do problem set 2 today. And I'll post a quiz later. And by you guys, you're submitting homework and quizzes, hard copies to me, right? And I think I mentioned yesterday that you shouldn't be able to do that on Sakai, but I might not have done that. But you know how to handle it, how we're handling it. What's that? Oh God. Okay. All right. So the first problem here is 7.4. This is pretty simple. We're going to use this expression for a plane wave. Now this is a general plane wave in 3 dimensions, right? K is the wave vector. It's moving in the K direction. And this is an exercise to actually show that sound waves are to verify that sound waves are longitudinal. By longitudinal, we mean, if the wave is traveling this way, the compressions and expansions, the particle velocity is parallel or anti-parallel. Particles are going back and forth in the direction that the wave is going. That's what a longitudinal wave is. Okay, so we begin with this for the acoustic pressure. And I don't remember if we're instructed to do it a certain way. Yeah, we're actually instructed to use the velocity potential. So we've used this several times now. This is for linear acoustics. This is the relationship between the acoustic pressure and the velocity potential. So the time derivative here just brings down, we replace the time derivative with I omega, as you can see. And we get this. We can then algebraically solve for the velocity potential. And we get this. It's easy. And now to get the velocity is the gradient of the potential. So how do I take the gradient of this? I don't know if we've hit this particular aspect before, but it's very similar to the time derivative. Because the time dependence is e to the I omega t, the time derivative, as I just mentioned, just brings down an I omega. Here it's going to bring down a minus ik. The gradient's going to bring down a minus ik. Now, this is not precisely identical to this. This is a scalar derivative. This is a vector differential derivative here. So if you have trouble seeing this, what you can do is look at the x component of this, right? The gradient, of course, looks like this, plus y and z. Look at the x component, and you'll be able to see then it is very similar to the time derivative, and it's going to bring down a minus ikx. It'll bring this down, but you'll have this attached to it, right? This will be there. And then you also have those other 2 terms. So when you put it all together, this is what you're going to find. That effectively you're replacing the gradient operator with minus ik vector. So we get this. So what we see here is that this is symbol for parallel to. The particle velocity is whatever the direction of propagation is, the particles are going to be moving parallel and back and forth, oscillating in that direction. So that confirms that the sound propagation is longitudinal here. Okay, any questions about that one?
So that first step, is that you're basically
the first step, this one?
And then, are you substituting and integrating? Is that how you get the...
No, this right here, I'm just taking the time derivative of this expression. And the time dependence is here. Right? So when you take a time derivative, you just get the exponential back, and you get I omega by the chain rule. That's all we're doing here.
Okay.
And this is similar. Oh, it's a little bit more complicated because it's a vector. But as I said, if you think of it as in rectangular components, it's essentially the same as the time derivative. Okay, any other questions about this? Okay, the next one is 8.1, and we're just going to do B. We have two plane traveling waves. They're going in the same direction. Okay? And they have different angular frequencies, omega 1 and omega 2. Okay? It's interesting here, we will also talk about the case when omega a little bit at the end, when omega 1 is equal to omega 2. But right now you want to think of this as omega 1 does not equal omega 2, and you'll see why when we get down here. So what these are going to look like, they're both going in the same direction. We'll call that the x direction. So here's our standard form for a plane wave. Now I'm going to use, to be careful here, this can be a complex amplitude, right? And the reason in general we want to make it complex is we can write any complex number as a positive real number here, the modulus, plus e to the I times some phase factor or argument, right? You know, we've discussed that. So if we substitute this into here, we're going to get a phi added to the phase factor here. All right, if I take this, substitute it into here, I get a phi added. Then when I take the real part, and we need to take the real part here because we're dealing with energy. We're going to be squaring this. So we've got to take the real part first. Remember that? So I get this, right? So this is the actual real expression. That's a weird sound. I wonder what that is. Pardon me?
I think it's a hammer drill.
Oh,
I don't know if it's called.
great. I wonder how long they're going to be there. Anybody know?
I heard a couple months.
A couple months? Well, that's not too bad. I just thought it was going to be like a year. Okay. Okay. So you can just look at this expression. This is a plane wave. It's only a function of x, traveling in the positive x direction. And in general, you know that we can have some amplitude, and we can always add a phase factor. And we're doing that just to be general here. Okay. And similarly, we have this here with two subscripts. Okay, to be general. General amplitude, frequency. And of course, omega 1 is equal to ck1, and omega 2 is equal to ck2. We have to obey that dispersion relationship, but we don't have a wave, a propagating wave. Okay, so the instantaneous, to do this part B here, the instantaneous energy density we showed for a traveling plane wave is equal to the instantaneous square of the pressure divided by rho naught c squared. We derived that. All right? Now, something interesting about this is if you go back and carefully look at the derivation and what went into the derivation, we made an assumption that it was a monofrequency wave. Okay? We don't have a monofrequency wave here. We have the sum of these two. Our wave is the sum of two monofrequency waves, which is not a monofrequency wave. It's got two frequencies in it. It turns out this is valid anyway. It's valid in general for any traveling plane wave. And we're going to prove that later on today. That's another problem. We're going to prove it. So right now we'll just assume it, okay? This is true for any plane traveling wave in one direction. So the total pressure is the sum of the individual pressures. In acoustics, linear acoustics, the pressure is additive. The particle velocity is additive, okay? The energies, as we'll see, the purpose of this problem is to look at the energies. But because they're proportional to square, you know they're not just going to be simply additive. You know there's going to be something going on there. But for the acoustic variables, pressure, particle velocity, etc., they're all additive. So the total pressure here, acoustic pressure, is the sum of the individual acoustic pressures. And now you can see the problem with the square here. We're picking up another term here. All right? So you can see right from here that the total instantaneous energy density is not the, here's when I multiply this through, this is the instantaneous energy density of the first wave, of the second wave. We get this extra term there, okay? It's because of the square. Now to analyze this, we're going to do the trick we did in lecture. We don't want to carry, this is kind of long stuff to carry along, so we're just going to call the arguments tau here. Tau 1 and tau 2. And an average over time will be an average over tau 1 or tau 2 and tau 2. So the average energy, when we average, see what's going to happen here. When we average this right here to get the average energy density, we get the average of P1 squared, which is going to be here, the average of P2 squared, which is here. And then we also get this additional term here, which looks like this. Now, what's this? What's the average of cosine squared? 1/2, right? You can see it, right? This is 1/2. What's this? Now, some of you might be able to see this, but I bet some of you can't. So let's just analyze it in the usual way to do it rigorously is with trigonometric identity. So here's the standard trigonometric identity for the product of two sinusoids expressed as a sum. So the average of this is going to now be this. What's the average of a cosine? 0, right? And what's the average of this? We have to be careful here. Tau 1 minus, what is tau 1 minus tau 2? You can see that it's going to involve the time if omega 1 does not equal omega 2, right? So because it's got a time in there, when you average, it's oscillating, the average is going to be 0. The average will be, so the average will be 0 on both of those. But for this one, for this term right here, well, we better finish the problem before we go on. So as long as the frequencies are different, you can see you're going to have an omega, a difference in the omegas times t here. So it's going to average to 0, obviously. So we get that even though for the instantaneous energy density, the total instantaneous energy density is not the sum of the individual instantaneous energy densities. We get this extra term. When we average over time, we do get the fact that the total average energy is the sum of the individual average energy densities. Okay? Any questions about that? Now, it's interesting to kind of think about this case, and I added something this morning. What happens when omega 1 is equal to omega 2? Well, now, when you take tau 1 minus tau 2, what happens? Now, time disappears. When omega 1 is equal to omega 2, and I look at the difference, this is tau 1, and this is tau 2. When I take the difference here, when omega 1 equals omega 2, oh, and that means K1 will have to equal K2, what do we end up with? Well, you can see that we end up with a phase, with this phase here. And, you know, this could be 90 degrees. The cosine here could be 0. This is a constant. But it's, in general, it's only restricted to this minus 1/2 going to to the interval, minus 1/2 to 1/2. It could be 0, but you're not guaranteed that. So in that case, we don't get the result. When the frequencies are the same, they're more coherent now. Here they're just averaging out. Those two different frequencies are averaging out in the cross product here. But it's in general, in general it doesn't, wrong button. In general it doesn't happen when the frequencies are equal here. And here's a very simple case. Suppose these are my two waves. They both have the same amplitude. They have the same frequency. They're both traveling in the same direction. But there's a 180-degree phase difference. Now, our theory will cover that, but forget the theory. What's the total instantaneous energy here, or average energy? It's 0. When you add a wave, when you add these two together, you get identically 0. However, the individual average energies are going to be this expression, as we've seen, as we derived in class, and we used it up there, or derived it. So, you know, here that's a clear violation of this result right here. The fact that the total average energy density is the sum of the intervals. We get 0 here and we get non-zero over there. Okay, so yeah, this is only true for when the frequencies are different. Okay, any questions about that one? Uh, 9.1. This is not real interesting. It's an exercise, but what we're going to do is for for this plane traveling wave here, we're going to find all of the acoustic variables, including the density swing, which we haven't discussed. You know, we haven't discussed it in here, right? But as you all know, it's on the quiz, right? In fact, I stated something on the quiz. We're going to derive it right here. I wanted you just to use that. You'll remember that you were told to use this on the quiz. We're actually going to derive it right now. Okay, so here's a plane traveling wave. This P, of course, means the acoustic pressure, which is the total pressure minus the equilibrium, the constant equilibrium pressure. So this is the change in pressure from equilibrium, right? That's what we mean by P here. It's how the pressure deviates from equilibrium. And in this problem, we're asked for the density swing. So that's similar to the pressure here. The acoustic density is how the density deviates from the equilibrium background density. And so this is, we can think of this as delta rho. Now the reason I'm putting in these delta quantities here is that we know that the square of the speed of sound is how the pressure changes with density. It's understood here that it has to be done adiabatically. You got to take this derivative under adiabatic conditions, right? Because the sound propagation is adiabatic. And then you need to evaluate an equilibrium. So I've dropped all those notations there, okay? But what we have here is, you know, we can think of this dP as a delta P, where delta P is small. And we think of this d rho as a delta rho. So as long as those deltas are small, which they are for linear acoustics, we see that I can multiply this through, thinking of these as small quantities. And we're going to get this. This will be true. Approximately true, and it's exactly true in the limit as delta P, delta rho go to 0. Typical linear acoustics is, these are so small, this is very good approximation here. So, but this delta P is just what we've been calling P, isn't it? Right? And the delta rho is what we're calling rho prime. So we just substitute those in there and we get this. And this is what I wanted, because we hadn't hit it yet, that's why I gave it to you on a quiz, right? So that's, you use that on the quiz. Okay, so the acoustic density is simply P over C squared, where P is the acoustic pressure. This is the acoustic pressure, so we get that. So that's the first part. Any questions about that? The next is the particle velocity. So how do we find the particle velocity? Well, what you want to start thinking is it's good for many reasons, and this is just one of them, to use the impedance, the specific acoustic impedance, which is defined to be the complex pressure divided by the complex velocity. So we know the specific acoustic impedance for a plane traveling wave. It's just rho naught C. So I can use this fact to get the particle velocity. This is the easiest way to do it. And things are going to get more complicated in this course, and we really want to use the impedance, as you'll see. And you could get this with a little bit more trouble. You could avoid the use of impedance here, but it's good to get used to it right now in acoustics. So it's just P over Z. Z is rho naught C, and we get that. That's the velocity. And this, of course, is the velocity amplitude, just as this is the acoustic density amplitude. Let's see, next is the velocity potential. We just discussed this standard relationship. We've used a number of times. And again, because this is a plane traveling wave in one direction, the time derivative just brings down an I omega. It just brings down an I omega from here, right? And so we get this. We solve for the velocity potential, particle velocity potential, and we get that. And you know, there's nothing wrong. There's an I there, and we discussed this briefly in lecture. And it's there for a reason. You know, when you take the real part of this, when you take the, assuming this P is real here, assuming that's a real positive, you're going to get a cosine wave here, cosine of omega t minus kx. What are you going to get here when you take the real part? Can anybody see it? Or can you guess? It's going to be a sine. It's 90 degrees out of phase. And you know, the way you see this is you just use this. Everyone should be familiar with this. I hope. Standard relationship here. Use that relationship. And this, because there's this I here, when you take the real part, that's going to switch you from the cosine. Without this, you would get to be taking the cosine here. But due to that, you're going to be, you're in it with a sine. It's 90 degrees out of phase. Okay, the instantaneous energy density for a traveling plane wave, we showed it in lecture, we showed it's equal to this. Remember, the potential energy has a 2 here, and the kinetic energy has a 2, but they're, for a plane traveling wave, they're the same. It's equal partition of energy, so when you add them, you lose the factor of 2. That's how you get this. Now, again, we want to take the, we're squaring this. You got to take the real part first. And I'm assuming P is a real number here. This P. And the real part's just going to be this, as we were just talking. It's going to be just a cosine wave. So you substitute it in and you get this for the instantaneous energy density. And now if we time average, the average of this is going to be 1/2, so we get this. And now we're back to having a 1/2 in there. But remember, this is the peak amplitude squared. What's this? The average of the cosine squared is 1/2. Oh, that's right. Yeah. Sorry. So, what do we see in our heads there for the average of the cosine squared? Right? When you take a sinusoid, any sinusoid, and square it, it becomes positive, and it's going to look, it's going to have twice the frequency. And well, I didn't do this. When we square it, it's going to be positive. And this is 1 right here. This is a sinusoid. This is a sinusoid, it turns out. We have there's a trigonometric identity that shows you that it is. And it's kind of interesting that when you square this, you get another sinusoid, but it's lifted, right? And so the average, once you realize that this is a sinusoid, you know that the average has to be 1/2. So that's why I wrote that in there, right here. Right, that's right. Okay, finally, the intensity. We derived this in lecture. This is the average intensity. We derived this formula in terms of the pressure amplitude. You can look back at that. Alternatively, and actually maybe the way we derived it, now that I think about it, you can use this very simple, and as I mentioned, it's almost self-evident relationship. The intensity is the energy density times the speed at which that energy density is moving. It's the speed of sound. So having found this, we can just multiply by C. And you see, if we just multiply this by C, we get that. Okay, any questions about this one? So here's this derivation. So let me remind you what I said earlier. If you go back, and I do this every year I teach this course, I say, did we really assume that it was a monofrequency wave? If you go back and look at our derivation, as I told you earlier, of the specific acoustic impedance or wave impedance of a plane traveling wave, okay? Going in one direction, that's what we mean by plane traveling, going one direction. This well-known result that it's rho naught c, which is analogous to a string, right? For a string, it's the linear density times the speed. We assumed, if you go back and carefully look at the derivation, what went into the derivation, we assumed a monofrequency wave. So it's more general than that, as I mentioned to you in that previous problem. And now we're going to prove it. This is kind of an interesting proof. It's you won't. Usually students don't find this real obvious. This is a thing that takes experience to see through this. It's simple, but it's probably the first time you've hit something like this. And what's interesting about it is we're being entirely general here. We just want to have, the only restriction is the disturbance is propagating in the plus x, in one direction, the plus x direction. So it can look like anything here. And this shape, whatever it is, just this continuous, smooth shape, it's got to be continuous and smooth, is just, it's like it's rigidly moving along at the speed of sound. So how do we mathematically describe this? Well, because everything's just, it's like it's just, if you think of this as some kind of structure, some kind of rod that you've bent, okay? You just take this, what's going to happen here is you just take that rod, that bent rod, and just rigidly move it along like this. So what that means is a point of constant phase here. Constant, you can think of this as pressure if you like. Point of constant pressure here is going to move with the speed c. And what that means is it's moving at speed c. So let's say, I think the best way to do this, let me say it this way. The best way to do this is, suppose this is some function of x, okay? Let's just assume for right now, and let's set t is equal to 0. Let's freeze this at time t is equal to 0. And let's let this, you can think of this as the pressure. At time t is equal to 0, this is going to be some function of x here, okay? How do I describe this disturbance at some later time? Well, the whole disturbance is just moving with speed c, right? Oh, I can see that we got a problem here. Sorry. We have to write it like this. It doesn't make any difference. All that's important is the difference here. We can swap these two. So unfortunately, I'm going to have to do it for this argument. I'm going to have to write it like that. Sorry. So at time t is equal to 0, we have this. A point on here of constant f value moves with speed c. So that you can see that as time goes on, to ride this wave, to be at a certain point on the wave here, to ride that point, just much like somebody who's surfing, right? You're going to have to move at speed c. So your x value, of course, is being incremented by ct. So this function right here will describe this shape. At time t is equal to 0, it describes exactly what you see here. And then as time goes on, it describes the fact that this just moves rigidly along. It's translated by the distance ct. So we leave this. We don't know what f is, but we know that it has to be only a function of one variable. When you write down a wave like this, in general, it's a function of two variables, x and time. But for a wave traveling in one direction, plane wave traveling in one direction, it can only be a function of this variable. If it was traveling in the left direction, we'd have a plus sign here. So this turns out to be enough to solve the problem, interestingly enough, okay? So again, we're using this for the pressure. We're setting this, sorry, I hadn't thought about this. We set this equal to the pressure, but we could just as well choose any acoustic variable. And we actually want to, you can see here, we want to choose the velocity potential. So it's the same, essentially the same. So we substitute this in here. Now, how do I take the derivative? I take the partial derivative of f with respect to t. What do I get? How do I do that? Well, I differentiate f with respect to its argument, which I'm going to call c here, just to be clear about this. I differentiate with respect to the argument, and then by the chain rule, I have to differentiate c with respect to time. So we're going to call f prime the derivative of f of c with respect to c, and now we have to differentiate this with respect to time. You see that it's going to bring out a c by the chain rule. So that's that c right there. Okay? So we're done with the pressure. We can't do this. We can't take this any further because we don't know f. What's the particle velocity? We're headed towards the impedance here. Particle velocity is the gradient of the velocity potential. We don't need vectors here. We're all in one dimension in the x direction. So the particle velocity here is the partial of phi with respect to x. And now what's that? Well, again, by the chain rule, I differentiate f with respect to c, so I get this f prime, and then I got to take this and differentiate it with respect to x, and that's going to bring out a minus sign, right? Because of that minus sign right there. And now that's our result for the particle velocity. We have the pressure result here. We take the ratio. And you can see when you take the ratio here, the f primes cancel, the minus signs cancel, and we get the impedance. So this is more general than what we derived in class. We've just showed here that it holds for any plane traveling wave, traveling in one dimension, in one direction. The impedance is rho naught c. I think they ask for, I guess they asked for a little more here. We proved this in general. There were no assumptions. Remember that? And I pointed it out and I edited it into the notes. You haven't gotten the edited notes yet. You will eventually. This is entirely general. There's no assumption here. There's only linear acoustics is assumed here. Remember that? We were very general about that. So you'll notice here what we can do is, now that we've established this in general, the general impedance, we can get rid of, for example, the particle velocity. We could substitute it for u here. We find that the energy, we have equal partition of energy, and we can use this formula. I guess this is what they wanted us to derive. The 2 goes away here because of the kinetic energy. And we get this, which is the same, of course, as the monofrequency result. Yeah.
My version of the book doesn't ask for the
density. Yep, there are different printings for this edition. Let me see, what problem is this? 10.2? This one doesn't too, but the one I have at home might. I don't know. I wouldn't worry about it. This is not a big deal. But my guess is it comes from I think I know. Okay, I think I'm wrong. I don't think this is a printing issue. I think I'm doing this to make contact with that previous problem that we did.
In your instructions, you asked
for
it separately.
Okay, I forgot about that. Yeah, okay. So this is just connecting it up with that previous problem. Okay, any other questions? Okay. So we got 2 more problems. All right, it's going to get more interesting now. And the last one is really interesting. I think you'll be amazed by it. The first one, these both involve spherical waves now, okay? So the first one is 11.2. We have a small source, and we're at a fixed radial distance of 10 centimeters. And we're going to compute, this is generating a spherical wave, and we're going to compute the phase angle between the pressure and the particle velocity. Remember, for a plane traveling wave, the particle velocity and the pressure are in phase. But once you go to a spherical wave, they're not in phase anymore, in general. So we're going to find that angle. We're going to make natural to make a table here. And we're also going to find the magnitude of the specific acoustic impedance. Now, why is that important? Well, that's going to tell us what the amplitude, the velocity amplitude is compared to the pressure amplitude. Okay, and it's for a plane traveling wave, there's this fixed relationship. And I'm going to add a plane wave, plane traveling wave here. The fact that the magnitude of the impedance changes means that the ratio of the pressure amplitude and the velocity amplitude is not constant here. It depends where you are, or in this case, we're fixing R and we're changing the frequency. So that's the game here, okay? It's different, they could have just scanned R. They could have let R go, but instead, I kind of see I think it's more interesting and simpler here. Here we're going to change the frequency. So we want to know these quantities for these different frequencies at this fixed distance. So let me remind you what we have here. We derive this. This is the specific acoustic impedance of a spherical wave. This is usually the expression we use. Although I understand it's not the one that Professor Baker prefers. He was telling me that yesterday. Okay. You guys remember this? Oh, no, you didn't. You couldn't have had this. Right. He was talking about the past. Never mind. Anyway, this is the one that KFCS used. This is the preferred form. Okay. Now, what's theta? Again, theta has nothing to do with the spherical coordinate angle theta, the polar angle from the z-axis, that angle right there. This is just the phase of the impedance. So it's going to be the phase between the pressure and the velocity. How do we get theta? We get it from the right triangle construction right here. This tells you what theta is in terms of the wave number and the frequency. And we know the wave number and the frequency are related by omega is equal to ck. Okay, so we're going to need to know we're asked for the magnitude of the impedance. That will, of course, be this. And you can see, as we discussed in class, the cosine of theta is just going to be kr over the square root of 1 plus kr squared. It'll be equal to that. And you can see here that the tangent of theta is 1 over kr. Okay, now I want to point something out. This is going to be important for the next problem that we're going to do. As I said, and as you can see here, the pressure and the particle velocity are not in phase. Okay, one leads the other. Okay, so I have an oscillator here. You can think of this as the pressure, okay, and this is the particle velocity. For a plane wave, they're in phase, right? For a spherical wave, unless you're really far away, infinitely far away in plane wave limit, right? There's going to be a phase difference. So what does it look like? Does the pressure, it's possible for the pressure to lead the particle velocity. See what I'm doing here with my hands? The pressure is leading the particle velocity, or it could be the other way around. So what it is here, I'm talking about it now, we didn't talk about this in lecture. If you look at the theory here, we have this e to the I theta. Theta is positive. It's restricted between 0 and pi over 2. Z is p over u, right? So you can see here that I can put the theta in the argument for the pressure, or I can put it in, either way, I can put it in the velocity. I can see here that I put it in the velocity. We're going to get the same answer. I'm not sure why I'm doing all this, but the point is this, is that because this angle theta is positive here, okay, we can write the pressure and the particle velocity like this, where this is a positive angle. This tells you that the velocity lags the pressure, which is physically reasonable because it's the pressure that's driving the particle velocity, right? We think of the pressure as the drive and the velocity as the response, just like we think of the voltage as the drive and the current as the response in a circuit. So the situation here is that if this is the pressure, let's say we look at a fixed time at some x here, then so this is the pressure. if I'm at a fixed point here, go to some fixed point in space right here. This wave is going over you. The pressure peaks out at a time. At a later time, the velocity peaks out. This is what we mean by U lags P. Okay? And it lags it by the angle theta. The phase angle here is theta. Okay. So I'm mentioning this here just because it comes up and we'll need it in the next problem. So now, how do we calculate all this stuff? Well, we've got different frequencies. Well, so we're going to know this frequency. That'll tell us what the wave number is. And we need, this whole theory is phrased in terms of Kr. R is fixed, but K is going to vary because omega varies. So Kr is the relevant quantity in the theory. That's equal to omega over C times R. And remember, omega is 2 pi f, right? Make sure you know that, okay? Especially when you do laboratory work, like this afternoon. So this is our Kr quantity. We know what R is. We know what C is. We're in air, room temperature. And now we can make our table. We're going to do these different frequencies, 10 hertz and going up in orders of magnitude. And like I said, I added the infinity here. This is going to be a plane wave. So you just punch these out with your calculator. Here are the values of Kr. We find theta from here. Once we get the values of Kr, we find theta, and we can find the magnitude from here. And here's what you get. Here's what you get for theta, and here's what you get for z. Now, two things to point out here. This is close to 90 degrees, isn't it? And that means we have, effectively, it's like a standing wave here. But it's not exactly 90. So there is some propagation of energy. We're going to talk much more about this in a later chapter. Also, there was something in the notes that I didn't point out yesterday. We're going to talk more about this, but I just want to get it in your heads. The fact that this is changing means that what is the, compared to the plane wave case, we have a particle velocity amplitude and a pressure amplitude. What kind of, what do we get here for the velocity amplitude compared to the velocity amplitude here? If the impedance is less, what does that mean? More response, greater velocity, yeah. And it can be huge. So what's happening here is the kinetic energy density is dominating the potential energy density. We're going to have much more to say about that in the few chapters away. Okay, any questions about this? Okay, so now this problem. This is an amazing problem. It's Navy relevant. So here's the idea. There's a source, and I guess we're in a medium here. I don't know. Air, thank you. It could be water, right? Doesn't matter. We have a receiver here, and this receiver detects a pressure amplitude and a particle velocity amplitude. These are the two numbers we get out of our receiver. And the question is, can we localize the source? Can we identify where the source is? This is called an inverse problem. Usually you have a source and you want to find out what the wave looks like, what you would detect somewhere else. This is the more practical, especially for the military, problem of, by making measurements here, can I figure out where that source is? And perhaps what it is, right? You guys are all familiar with this. All right. It's standard in radar, and it's acoustics too. So let's see what we can, how can we approach this? Well, we're going to have a spherical wave here. We know for a spherical wave, I didn't bring my liquid, that the impedance is equal to this. Okay? If we take the modulus of this, then we get this relationship between our amplitudes, our peak amplitudes here. We've seen this before. Okay? Now, what can we do? Well, we can determine theta, right? We got one equation and one unknown, so we should probably just go ahead and do that. So we solve for theta, I get this expression, plug the numbers in, and I get that for the cosine of theta. I take the inverse cosine, and I get about roughly 60 degrees, 61.2 degrees. So what does that tell us? That tells us the phase angle between the particle velocity and the pressure. And that means if we know the frequency, which we know here, and it's easy, the receiver here will also be detecting frequency, right, in any practical situation. No problem with frequency. Okay? So we know the phase angle, we know the frequency, and you can see from the right triangle construction here that we can find the tangent of theta has to be 1 over kr. So we can find r. We can find r with our 61.2 degrees. Plug it in. Well, I found kr. We have to divide by k. K here is omega over c, right? So we went through a similar. We go through this a lot in this course. Okay. I plug the numbers in. I can find the distance. It's a small distance. It happens to be 30 centimeters. Okay. So with just these two measurements, we can tell what can we say about the source? What can we say? We don't know where the source is. That's the game here. We can tell how far away it is, which means we've localized it to a sphere concentric with the receiver of this radius. Okay, we've narrowed it down that it's on a sphere. Okay, now what other information will we need to try to actually figure out exactly where it is? Okay, well here's the way, that's what they're asking here. So here's the way I look at it, all right? And I don't know if I've seen theirs. Anyway, this is the way I look at it. As far as I know, any detector that detects particle velocity, and these are hot transducers these days for the Navy, because it gives you, if you're going to detect particle speed, you're almost certainly going to be able to detect a direction, okay? That's my knowledge of velocity transducers is, acoustic velocity transducers is, you're going to find the direction. Now, you're not going to know, you're not going to know if the wave is coming from here or from here, but you've got this transducer, and the way it works is, for a hot wire microphone, for example, we'll talk about those later. If not in this course, definitely in the next course. I've got my detector here. It's going to have directionality. It's going to be a maximum when I'm aligned with the particle motion. Okay, that's the standard thing. So, assuming we have that, now we've ruled out everything on the sphere except what? So suppose we realize that the particle velocity is moving this way. Now what have we narrowed the source down to? Here, 2 points. I heard somebody say it. This point or an equidistant point over there, right? So how do we narrow it down to 1 point? I can't hear.
Your impedance sample?
Yes, it's natural. That's right. It's natural to look at the phase. Now this is a little tricky, and if you don't get it, it's okay. But let me go through this. Here's the way that I present this. Okay, and this has evolved over the years. Okay, and I think I edited this just last year too. We're picking up on a sound wave here. Let's call this the positive x direction. We're not making any assumptions here. We're just going to call that the positive x direction. Okay. Once I do that, I need to assign a direction, because when I'm plotting u here, this is a positive u. So for me to make sense out of this graph right here, I've got to pick the dashed line here. The pressure doesn't matter. It's just a scalar, right? But this is really a vector. So it's got directionality. So for me to actually see this curve right here, I got to pick a positive direction. So I choose this to be the positive direction. And with my transducers, if I see u lagging p, then we can conclude that the source is here. But I may not see that. The other possibility is that we see p lagging u. In that case, what do you think is happening here? We need the sources on the other side. Now, this is not real obvious, and I struggle with this every year that I teach this. Like I said, I've just modified it. But I've convinced myself of that. And if you're interested, see me or contact me, okay? But I'm sure this is right, okay? So that's what you can do here. You can assign this to positive direction. If you have the correct relationship here with U lagging P, then that will be the positive direction from the source. If it's not, the source will be on the other side, okay? Now the final interesting thing here is this. This seems like the Navy ought to have these things. This is great. Now, do they? Okay. No. I'm talking about the Navy should employ this technique to localize a source.
Well, that's what we do. What are they starting to?
Okay, well, I'm suspicious, okay? And here's why. Typical application is, this is going to be nearly a plane wave. I would think, in typical applications. I don't really know. You may know better than me. You probably know better than me. So,
working ranges of 30 centimeters.
well, this frequency could be much greater. We don't know, right? Yeah, 30 centimeters is crazy, but my guess is that for applications, this is going to be nearly a plane wave, and you've got a big problem when it's nearly a plane wave, okay? Because KR, the thing you're after here, that's going to give you the distance, right? Is 1 over the tangent of theta. For a plane wave, theta is going to be close to 0. And there's going to be some uncertainty in your measurements here. Remember, we got theta from these two measurements right here. A little bit of uncertainty there. A little bit of uncertainty in the theta around 0 makes a big uncertainty here. This is blowing up. This is like 1 over 0. The tangent of 0 is 0. So it's going to be very sensitive. So I'm suspicious about the practical application of this. But I'd love to know more about it. So if anybody's interested or you know anything about it, let me know, okay? Including the distance learning students. Maybe they know about this. It's fascinating, though, isn't it? It's interesting. It sort of justifies spherical waves right there. There's just this one problem. But we're going to get a lot more use out of spherical waves, as I told you. Okay, any quick questions? Okay, Monday's a holiday. Does everyone know that? To be honest with you, I have no idea what holiday it is. I don't really care. What is it?
Columbus.
Oh, Columbus Day, yeah. The really important holiday. Okay, so we'll pick up lecturing on Tuesday. One more lecture on this chapter.